All right, chemistry. Here's part 2 of your video lecture for chapter 2, section 3, using scientific measurements. Last time we talked about accuracy and precision, and we also introduced the rules for determining number of significant figures. To that end, I'll go back to that slide just as a refresher. Rule number 1, any non-zero digit is always considered significant. Number 2, zeros between non-zero digits are considered significant. Sometimes I'll refer to these as sandwiched zeros or captured zeros. Number 3, any zeros that are in front, meaning to the left, of any non-zero digit are never considered significant. Trailing zeros, however, the zeros that are on the right of any non-zero digit, you have to look and find, is there a decimal present or not? Because any trailing zeros are only significant if there is a decimal present in the number. Any trailing zeros are not significant if there is no decimal in the number. So moving on, in part 2 of the video lecture, I want you to be able to apply those rules for significant figures in calculations. And then I want you to be able to write very large and very small numbers in scientific notation. So here we go. Now, one thing that you guys need to understand before we get started talking about calculations and significant figures, when you use a calculator to find a result for something, you have to pay attention to significant figures because the calculator does not round the result to the correct number of significant figures. Now, the reason that is because the calculator is operating under the assumption that you are using an infinite number of significant figures, and so it doesn't consider that for you. So even though your calculator spits out 9 digits for a result, that doesn't mean that you should be writing down all 9 digits for your result. Similarly, if it only gives you 1 digit, that doesn't mean that there aren't more digits that are significant. So you can't trust your calculator to help you with significant figures. You are the one that is going to have to apply those rules. So again, to determine the number of significant figures in the answer, you must first find the number of significant figures used in the values used to calculate the answer. Okay, so looking at your calculator, how many significant figures you're going to report from that particular answer depends on the number of significant figures that were present in the values that you used to calculate that value. So with multiplication and division, the answer cannot have more significant figures than the measurement with the smallest number of significant figures. So you're multiplying two numbers. Look at which of those two numbers you're multiplying. Identify which one has the fewest number of significant figures. That is the number of significant figures that your answer needs to have. With addition and subtraction, it's a little bit different. The result can have no more certainty than the least certain number in the calculation. So when you're doing addition and subtraction, you need to look at the numbers that you're adding or subtracting and identify which value has the fewest digits past the decimal place. Okay, past the decimal place. Whichever has the fewest, that's how many digits past the decimal place your answer should have. Now, if the calculation has both addition and subtraction, both addition and subtraction and multiplication or division, you need to round after each individual operation. Okay, after each individual operation, figure out how many significant figures you have before you move on for each intermediate step. Now, there is going to be something that could throw a little bit of a wrench in the system here. There's something called exact values. Okay, exact values. Some values have I like to call them an unlimited number of significant figures. These exact values have no uncertainty. One type of exact value is a count value, which is determined by counting, not measuring. Something really easy, something like, how many cars are right there? Well, there are 3 cars right there. Now, that's not, the number 3, that measurement 3, does not have significant figures associated with it because it's exactly 3. It's exactly 3. There's not, you can't have 3.1 cars, 3.2 cars. You have 3 functioning cars, that's a count value because I determined it by counting, not by measuring. Another value that can have an infinite number of significant figures is a conversion factor. For example, when you are doing calculations converting from number of grams into number of kilograms, you are using a conversion factor that said that 1 kilogram is equal to 1,000 grams. You are not limited by the 1 for the 1 kilogram. That's not meaning that you're only going to use one significant figure or the 4 digits from the 1,000. Those are exact numbers. They're considered to have an infinite number of significant figures. Another way of saying that is that they're involved in a definition. 1 kilogram is defined as 1,000 grams, and so you don't have to worry about those in terms of significant figures. So ignore both count values and conversion factors when determining the number of significant figures. Let's try a sample problem here. So a student heats 23.62 grams of a solid and observes that its temperature increases from 21.6 degrees Celsius to 36.79 degrees Celsius. Calculate the temperature increase per gram, right? So this is a per gram of the solid. So first off, I'm going to calculate the increase in temperature by subtracting the initial temperature, which is the 21.6 degrees Celsius, from the final temperature, the 36.79 degrees Celsius. That might seem kind of simple, right? The temperature increase is the final temperature minus the initial temperature. Fair enough. And so I generate an answer of 15.2 degrees Celsius. Now, I'm not done yet, right? Because the question asked me for temperature increase per gram of solid, right? And so the total temperature increase is 15.2 degrees Celsius. Now I need to do something about the per gram part. So I'm going to calculate the temperature increase per gram of solid by dividing that temperature increase, the 15.2 that I just calculated, by the mass of that solid, which was 23.62 grams. Again, that was given to me by the problem. And so the temperature increase divided by the number of grams is the temperature increase divided by the sample mass. And so I'm going to take the temperature increase, divide it by the sample mass, and I generate an answer of 0.644 degrees Celsius per gram, right? Per single gram, each gram of this sample has had a temperature increase of 0.644 degrees Celsius. Now, because I'm doing division here, I'm going to consider 1, 2, 3 significant figures, and then 1, 2, 3, 4 significant figures. Okay, that's 4 significant figures there, but this top value has 3, so my answer is going to be communicated with 3 significant figures. Moving on to scientific notation, this is going to be how we satisfy our objective of writing very, very small numbers and writing very, very large numbers. So very large and very small numbers are often written in scientific notation. A number in scientific notation has 2 parts. The first part is a number that is between 1 and 10. This is called the coefficient. Okay, the coefficient. So if you hear me use this term, that's what I'm talking about. It's the number in front, and it will always be between 1 and 10. If that number is not between 1 and 10, that number is not in proper scientific notation. Doesn't mean it's not a number. Okay, it can be a real value. It still has meaning. It's just not in this specific type of notation known as scientific notation. The second part of a number in scientific notation is a power of 10, an exponent. An exponent, a power of 10. And it's always to a power of 10. If it's to a power of like 7 or some other number, it's not in proper scientific notation. Doesn't mean it's not a number, not a real number. It's just not in proper scientific notation. So to write the first part of the number, you have to move the decimal right or left so that only one non-zero digit is to the left of the decimal. Think about it. That's what it takes to have a number between 1 and 10. It can't be 10, right? At the very highest, it has to be 9 point something, right? On and on and on. But you're only going to have one non-zero digit to the left of the decimal. Write the second part of the value as an exponent. This part is determined by counting. Again, counting, that would be a count value, not considered in significant figures. This part is determined by counting the number of decimal places the decimal point was moved to go from the standard notation into the scientific notation. If the decimal is moved to the right, the exponent is negative. If the decimal is moved to the left, the exponent is positive. In scientific notation, exponents are count values, like we already mentioned. Okay, you're counting how many places the decimals move, so it doesn't get taken into consideration for significant figures. In addition and subtraction problems, all values must have the same exponent before they can be added or subtracted. The result is the sum of the difference of the first factors multiplied by the same exponent of 10. Meaning before you can add or subtract two numbers in scientific notation, you have to change the exponents so that they are the exact same exponent. Then you simply add or subtract the coefficients like normal. In multiplication problems, the first factors, the coefficients of in the numbers, are multiplied. Okay, obviously it's multiplication. But when you consider what to do with the exponents, you simply add the exponents together. You add the exponents together. In division problems, obviously the coefficients are divided, but in division, the exponents are going to be divided. Okay, the exponent of 10 in the denominator, it's going to be subtracted. The exponent of 10 in the denominator is subtracted from the exponent of 10 in the numerator. So let's look at a sample problem. So if I have my sample problem of 3.2 times 10 to the negative 3 multiplied by 2.1 times 10 to the 5th, okay, I need to make sure I understand I'm multiplying here. So when multiplying numbers written in scientific notation, multiply the first factors or the coefficients and then add the exponents. So the first thing I'm going to do is I'm going to multiply the 3.2 by the 2.1. So that part is easy. But what I'm going to do with these exponents, I'm going to add them together. So that means I'm going to take the negative 3 and add 5. Right? Negative 3 plus 5 is positive 2. And so my answer is actually going to be 6.7 times 10 to the second power. Let's try another one. But here we're going to divide. So when dividing the numerator by so we have a numerator and a denominator, just like a normal division. Subtract the exponent in the denominator from the exponent in the numerator. Okay. From here, you're going to divide the 6.4 by the 1.7, just like normal. But I'm going to take that 6. I'm going to have 6 minus 2, right? I'm going to take that 2, subtract it from 6, right? Because it's on the denominator. I'm going to subtract that from the numerator. And so what I've actually done to generate this answer of 3.8 times 10 to the 4th, I obviously have divided the 6.4 by the 1.7, but I've also subtracted the exponents, 6 minus 2. Let's go through one more. We're going to do some addition here. So to add or subtract numbers written in scientific notation, you must express them to the same power of 10. If you have a sample problem, for example, 5.8 times 10 to the 3rd plus 2.16 times 10 to the 4th, I am going to first make sure that the powers of 10 are the same. So here, since the two numbers are not expressed as the same power of 10, one of the numbers will have to be rewritten in the same power of 10 as the others. Okay, so I have times 10 to the 3 and a times 10 to the 4th. I can't add these yet. And so what I'm going to do here is I'm going to move the decimal on one of the numbers, and so that that exponent will change until it's the same on the other value. Now, it does not matter which decimal I decide to move. If I want to move the decimal in the times 10 to the 3rd value or the times 10 to the 4th value, it truly does not matter. And so in order to complete this example, I've chosen to move the decimal in the times 10 to the 3rd value, and I'm going to move that decimal one place to the left. And so what I'm actually carrying out here is 0.58 times 10 to the 4th plus 2.16 times 10 to the 4th. Now, when I'm adding, I take my 0.58 plus 2.16 just like normal. Okay, that part doesn't change. Now, when I'm adding my times 10 to the 4th, that does not change here. It does not change at all. It just stays times 10 to the 4th, and so my final answer is 2.74 times 10 to the 4th power. So what we've accomplished so far in this section, and you're going to be responsible for the quick write and the quiz. Distinguish between accuracy and precision in measurements. Distinguish the number of significant figures in a measurement. Apply the rules for significant figures in calculations, and then write very large. Apply rules for significant figures in calculations, and then write very large and very small numbers in scientific notation. All right, chemistry, I will see you next period.